Welcome to the Explainer. You know, we write code all the time, but have you ever stopped to think, when I declare a variable in Java, where does it actually go? Well, today we're going to pull back the curtain on Java's memory model and find out exactly that.
So let's just start with that big question right there. Because honestly, the answer is so much more than just a fun fact. It is absolutely key to writing Java code that's efficient, solid, and a whole lot easier to debug.
All right, here's our game plan for this explainer. We are going to follow a variable on its entire journey through memory, right from the moment it's born to the moment it gets destroyed. Okay, so first things first, whenever you hit run on a Java program, the Java Virtual Machine, the JVM, it goes to your operating system and carves out a big chunk of memory for itself. It basically builds its own little universe to run your code in. And inside this universe, there are these two main neighborhoods where all your data is going to live. You've got the stack and you've got the heap. And trust me, each one has its own vibe, its own rules, and they're built for very different things. Now, before we can figure out which neighborhood our data moves into, we have to know what kind of data we even have. And in Java, it really all boils down to just two fundamental categories. And right here, this is the most important distinction you got to get. On one side, you have primitives. These are the simple things, right? They hold their value directly. Think of the number 42 or the Boolean value true. But then you have reference types. These are more like a claim ticket. They don't hold the actual thing, they just hold the address of where he can go find it in memory. So these are your absolute basic building blocks. Integers, decimals, true or false, a single character. The really important thing to remember about them is that they all have a fixed, predictable size. And that, as you're about to see, is what makes them so ridiculously efficient to work with. So, where do these super efficient little primitives live? Well, most of the time, they end up in a place called the stack. You can think of the stack as this highly organized, blazing fast, but pretty temporary workspace. Just imagine the stack is, well, a stack of notepads. Every single time your code calls a method, a brand new notepad, we call it a stack frame, gets slapped right on top of the pile. And that frame is that method's own private little world. So check this out. When you declare a primitive variable, like our int count, inside of a method, it gets stored directly inside that method's frame, right there on the stack. The variable count and its value 100, they live together in the same spot. This directness is what makes getting to it so incredibly fast. Okay, but what about all our other stuff? Our more complex data, our objects. I mean, they can be huge. Their size can change, and we often need them to stick around longer than just one single method call. They're just too big and unruly for the stack. They need a bigger, more permanent, more flexible home. And that home is called the heap. And here's the trigger, the thing you have to look for. Anytime you see the new keyword in Java, a little bell should go off in your head. That is your signal that an object is being built and placed out in that big shared memory warehouse we call the heap. Okay, so here's where it all comes together and the two worlds start to cooperate. The variable name, our little claim ticket that lives on the stack inside the method's frame. But its value isn't Hank. Nope, its value is a memory address, a pointer that tells you where to find the actual string object which is living way over on the heap. Now the stack gets its name because of its super strict behavior. Last in, first out, or LIFO as you'll hear it called. It's a really simple rule, but it is the perfect way to manage the flow of your entire program as it jumps from method to method. It works exactly like a stack of dinner plates, right? You can only put a new plate on top and you can only take a plate off the top. So when one method calls another, a new frame gets pushed onto the stack. And when that method is all done, its frame gets popped right off and control goes back to the method that was just below it. Simple as that. And here is the absolute magic of the stack. It cleans up after itself. The second a method finishes and its frame is popped off, everything inside that frame, all its local variables, is instantly and completely wiped away. It's automatic, it's immediate, and it's what makes the stack so incredibly efficient. So, okay, we've gone through all this. Why does it actually matter? It matters because understanding this core difference between the fast, orderly stack and the big, flexible heap is one of the most important things for writing Java code that performs well and doesn't have mysterious bugs. This table really just lays it all out. The stack, small, super fast, but its data vanishes in a flash. The heap, it's huge. Your data can live there for a long time, but it's slower to get to. And look at that lifespan part for the heap. It's managed by something called the garbage collector. See, unlike the stack's automatic cleanup,
The JVM has to run this special process to go hunting through the heap for old objects that nobody needs anymore. And that process, well, it takes time and energy.
So let's wrap this up. The key things to burn into your brain are primitives and those little reference variables live on the fast, temporary stack. The actual objects themselves live in the big, shared heap. The stack is all about managing method calls, last in, first out. And knowing this isn't just theory. If you create way too many objects on the heap, you'll make the garbage collector work way too hard and slow your app down. And if you have a bug where a method calls itself over and over, you'll run out of stack space and get that infamous Stack Overflow error.
So the next time you sit down to write some Java, just take a second and think, where is my data actually living? Is it on the fast, fleeting stack or the vast, persistent heap? Because really, understanding how memory works is a massive step towards becoming a truly great software engineer. Thanks for watching.